Good afternoon, everyone. Let me just make sure my microphone looks like it's a bit quieter than normal. Let me just check my sound settings. Oh, no, that's not what I wanted. That's the one. It's only 5 less than normal, so it might just have been my voice. Also, you can see we've got a little guest here already today, so your dosage of cat is already has already started. Um, People asking some things. Kyle is asking, doesn't matter if your crack substitution is really slow. No, it doesn't matter at all. We're not checking efficiency in this particular course, and especially for something like crack substitution, that is a very, very difficult task, so it doesn't matter if it takes a while to do it. I think the sample solution, which is written by one of the old subject admins of this course, still takes some time to work, so it does take some time to do what it's going to do, in a way that we often don't even notice that programs take time, because a lot of the programs that we've been running in COMP1511 have just done their thing immediately. I think the only program that I've run in COMP1511 that took a significant amount of time to run was the one where I did an infinite loop of allocating memory, because I was just allocating so much memory, it took a while for my computer to actually perform those operations. So I wouldn't worry too much if something's taking a while. I think even if you're attempting crack substitution at all, then you're taking on a mighty challenge. So don't worry about how it finishes. I think someone's decided that my lap is the warmest spot for today, and I fully understand that. You're saying, shouldn't it be good morning? I should have said good morning. Feels like late at night at the moment, though, but I think it's probably because I've been doing a whole lot of work today on other things. So let's get back to these slides. Oh, one thing I should point out, if anyone's interested, the much hyped Daniel Mansfield and Charlotte versus Marquis and Chicken stream is going to happen. It's not a versus, we're friends, but we're gonna actually have our cats meet each other. Then they're gonna have no idea what's happening. We're gonna try to have both cats on stream, and we're gonna do a little bit of like an AMA, they call it, on, I think Reddit was the first place they did AMAs, which is like an Ask Me Anything, which is, if you want to ask questions, you can ask questions. We'll both try to answer the questions for you. Let me just send you the link. I'll put the link in the chat at the moment. If you can't use that link from here, I also put the link on CSC Socks Facebook. I just wanted to keep it, like, I didn't know where else I could sort of broadcast that without getting to too many people, so I just put it there. And so Daniel and I are going to do a bit of a stream tomorrow night. It's pretty chill, just hang out. We're gonna answer your questions and things, and that's it. We're not doing anything big or formal or anything like that, just to hang out. So people are talking a little bit about the lab this week, talking about cracking a cipher. If you were trying to crack a substitution cipher, this is what Liang Chao's asking. So a substitution cipher is a method of cryptography where cryptography is the ability for us to hide what we're saying, in a sense. It's always been something that's kind of interesting to computer science, because the field of computer science got a big boost in World War II based on cryptography. So it was based on trying to use computers to break codes. So Alan Turing, who I told you about, I've mentioned in several lectures now, was one of the people who was one of the main people, I guess, working on code breaking at a place called Bletchley Park in the UK. And so there's a bit of us always kind of loving the idea of cryptography, and it's kind of fun as well because when you do a lot of programming, you look at like systems and trying to unpack what is in a system and how it works, and cryptography is like that. It's this system and this problem. You go, how do we unpack it? So the substitution cipher is that, say, any letter that I could write, instead of writing that letter, I write a different letter. So the Caesar cipher, which is the earlier stuff in the lab, is that every letter is offset a certain amount. So if your Caesar cipher is a 1, every A that you type in becomes a B, every B becomes a C, and so on through the alphabet. Substitution cipher is not as direct. It's not an offset. It can be any letter becomes any other letter. So to crack something like a substitution cipher is a little bit harder because you need to, in a sense, you need to lock down which letters mean which other letters. And you can really only do that if you have enough text to make some educated guesses as to which letters should be which. And one of the ways that we talk about doing that is by a frequency distribution, which is to say, for example, in the English language, just generally in the English language, the letter E turns up more than anything else. So if you've got enough letters that you can do a decent statistical analysis of how many letters are in the piece of text and how many and what's the frequency of each letter, like how many times does each letter appear, then you can start trying to do an analysis to try to unpack the fact that it's English. It's not easy, and it's not necessarily going to be correct, because you could do a frequency analysis on the English language, and then you can do a frequency analysis on a particular document, and it won't always be the same. But it can get you some clues, and it might get you enough so that you can pick out certain words. If you can pick out certain words, it gives you clues to other letters, and then those clues will build up into clues to other letters as well. It's quite a full-on process, and that's why getting a computer to do it is usually going to be a lot quicker than a person. But if you understand the theory, you can sort of get a computer program to do it. So it's interesting, it's fun. It's not necessary to. I should also say the warning, the warning for, I think it's crack substitution, right? The very final challenge in this week's lab is that it is definitely harder than freefall. So I think one of the sample solutions I've seen for it is about 1,000 lines of code, and this is 1,000 lines of code written by one of your tutors, so it's actually reasonably efficient. There's no repeated code in that. So it's a kind of a try at your own risk sort of thing. Kyle's saying trying to submit it, but the auto test takes 8 minutes. Yeah, that might be the case. That's alright. I mean, it's a challenge. Even if you'd never submitted it, you'd probably still get full marks in the lab. I'm not sure. Liang and Kyle are having a conversation about random things that have been happening there. Oh, hey Shrey, how's it going? Liang saying took you 2 hours to understand the starter code. Yeah, it can be a bit like that. Okay. Good morning, Reese. Okay, let's get started in what we're going to talk about today. Good morning, SK also. Today we are going to start building a data structure that is going to carry us through till the end of the term. So, I mean, we're in week 7, so we are in the final quarter of the course, I guess. So there's not a huge amount more of new and difficult topics I'm going to give you, but this is one where we're going to tie together a lot of what we've done before. So last lecture on Tuesday we looked at memory and we looked at allocating memory. We're definitely going to be using that today. We also looked at multi-file projects. That was something I was going to prep you for because the assignment release, which is impending, the assignment, well, you've had your 1 week off from the assignments, and so the next assignment release actually has a multi-file project in it. So that's why I covered it this week, so that at least when you see the assignment code for the first time, you're not like, what even is this H file and where does this stuff work? So I wanted to at least show you the beginnings of how to use that. Memory, we're definitely going to be doing a lot more allocating of memory, and so today we're going to start using memory allocation with structs. So we've seen structs a little bit, we've seen memory allocation a little bit, we've seen pointers more than the other two, I think, but not even then, not a huge amount. We're going to be using all of that stuff together now. So if you don't know some part of that, some bits of it, it's probably not a bad time after the lecture to go back and figure out what those things are from previous lectures. But what I'm going to do is I'm going to start tying this stuff together, and there's going to be a combination of sort of this theoretical idea of how we build a big connected collection of data out of these kinds of smaller constructs that we've had together. So it's kind of like the past month I've been teaching you about individual Lego bricks. So I've been teaching you just about these individual Lego bricks and how they work and how they connect to each other. And now we're going to start piecing them together. And when we build them together, we can get much more complex and much more interesting things. So that's where we're going to be. That's what we're going to be doing. I should have actually gone to this slide today when we were talking about. Anyway, that's going to be linked lists. The other thing I'm going to talk to you about today is something that is handy to know. Won't come up all the time, but it's something that I do want you to know about because it's one of the ways that programs tend to run a lot of the time. That's called command line arguments. That is the ability to, when we do /program, whatever the program name is, we can type in other words after that. And the other words we type in after that can be used inside the program. So we're going to just see how that works, so you get a look at it. But then we're going to spend probably the majority of the time on linked lists. So linked lists, I mean, we can consider an array if we wanted to. We could consider an array a list of variables. I wouldn't say list with a capital L. There is a technical term, list, which is a technical programming term which has a certain meaning. But you could still think of it as a list of objects. A linked list is also a list of objects. But instead of the way that arrays work and some of the restrictions, I guess, that are on arrays, a linked list has less restrictions. It's got more flexibility. You can insert and remove objects in between other objects. So we weren't really able to do that with arrays without copying a whole chunk of the array and moving it. It can be any length as well. Well, obviously the maximum length is going to be somewhere around 8 gigabytes worth of information, as we found out on Tuesday. But it does have the ability to change its length as you're using it, which is something that arrays didn't have either. So there's this kind of flexibility that we're going to get out of the linked list. One could, if you were talking only about flexibility, say that it is just flat out superior to an array, but there's still reasons to use both in different circumstances. So we're going to be learning about this. Also, it's just flat out harder to use a linked list than it is to use an array. So that's why it comes second. But it is a very, very important fundamental data structure for computer science. Like the linked list is the basis for graphs, and graphs are connecting data together. I'm hand waving this, right? I'm not giving you a full definition of this because we will learn linked lists before we even talk about that. So we're not even going to cover these things in this course. We're just going to get you on linked lists. But a lot of the hype nowadays around artificial intelligence, deep learning, and stuff like that is around neural networks. And the linked list could be considered the very, very most basic structure that builds up into the kind of structure that a neural network is. So this is us giving you, I mean, name of the course is Programming Fundamentals, so this is giving you that fundamental that then builds up into that. Shrey says this is his favorite part of the course. Oh, there you go. And Shrey's confirming, did use a linked list today while working in other subjects. So this is definitely something that builds further into other things. I mean, like linked lists and arrays are things that you're going to see in all programming because we use collections of data a lot. So, quick recap, because we're about to talk about strings, so I thought I'd do a quick recap of characters and strings. This is that thing I do all the time, right? I want to bring you back to things that we've done before because that works quite well for your memory. So, character, variable type. I guess I wouldn't really call it a new variable type anymore, but it's one of our newest variable types, and it represents a letter. The letter is also an ASCII code, which is the particular encoding of that letter. If you wind it back to the days of electric typewriters, where they actually sent that signal from the key to the other part of the typewriter, so that it would like press a little metal thing into the paper through an ink ribbon, right? So it's pretty old school, but we still use it because even if it wasn't intended for computers, it's an easy way to distinguish all the keys on the keyboard. One of the nice things about that is if we do want to use letters like their numbers, we can do that, because we do have a guarantee that every character is going to have a numerical value, and if we only look at the letters A through Z, either lowercase or uppercase, they're actually in numerical order of the alphabetical order. So there are little things like that we can do where we can actually add two letters together and get a result out of them. When we combine our letters together, we call them strings, and they are simply an array of characters. The thing that makes them a little bit fiddly, but also reasonably useful, is the fact that when we're storing a word, as opposed to storing an array of numbers, when we store an array of numbers, it's usually like, okay, we're storing these 10 numbers. You know, when I say I need an array to store a word, I don't know necessarily how long that's going to be, because you think about all the words in just English, like not even any of the other languages, just English. We've got a variety going from single letter words up to, I don't know what the longest word in the English language is, but it's probably like 20 or 30 letters or something. So we can't necessarily say for certain what length our word is going to be. So instead what we'll usually do is we will make an array of characters that's very long, longer than we need, but we use this character, the null terminator, to sit somewhere in that string to say, up until this point of the letters we care about, then we hit the null terminator, and please disregard the rest of the array. It was there as extra space in case the word was going to be longer. So every valid string in C is going to end in the null terminator. So we're going to have all the letters we want, and then we're going to end up with the null terminator that says, okay, stop reading letters here. This is where we go to, and this is all we need. A little bit of looking at strings in code. Both of these ways to initialize a string are going to work. So string has a shorthand. This makes it a little bit easier than typing all of this out when we're making a string. And we've seen this shorthand because we've been using this shorthand with printf for quite some time. So when we have either of these strings, this shorthand's automatically going to give us a null terminator. This way of doing things, we'd have to put the null terminator in ourselves. If we're going to be editing these strings, we probably want to be careful to make sure that we put a null terminator in if there isn't one, or we use specific functions out of the string library, and they're always going to give us a null terminator on the end. So, command line arguments. The line at which we were typing things in the terminal is referred to as a command line. So this is where we type in commands. So for example, ls is a command that tells me what's in the directory that I'm currently in, so listing of the files. Mkdir, make directory, is a command also, and all of these are typed in on this line with the prompt that's called the command line. So arguments are considered to be inputs to something. So we can consider, if I make a function that takes in an array and an integer for the length, I consider those to be the arguments of the function. So we call them inputs, arguments, and parameters. Like, we call them lots of different things, but arguments is one of the words for it. So when we get this situation, command line arguments, what we're saying is we could, if we wanted to, run a program and type in extra things afterwards. And we want these extra things afterwards to be put into the program somewhere for us to be able to use. So this is just a slight change in how we would set up our program, but we can set up our program so that we can actually get all this information. So all this information goes into the program, and we can use these particular words as if they're variables inside the program. So one of these things, one of the nice things to do with these command line arguments is they can allow us to, in a way, do our setup of the program before the program starts. So I've done several examples that had stuff like hash-defined constants or particular things that you needed to read in before you could do any other work with the with the program itself. Sometimes if we give this setup as the running of the program, it's easier for a person to understand it, because they say, okay, I'm going to run this program with these settings. And then you can go, okay, the command to run the program with these settings was to run the program and then put this text afterwards, and then that would always set up the program the same way. So that's often how command line arguments are used. Sometimes when we get down to it, command line arguments will be the files that we're working on. So if we consider a program, I don't know if it's technically a program, but I think it is, say, the cp command that's going to copy one file to another location. It takes two command line arguments. First one is the source file, and the second one is the destination location. So the way that that program would work is you would run cp, and then you'd have two strings that came after that, and those strings would actually go into the program where you say, okay, this file name and this file name. Now we need to go find those files and copy one to the other location. So that's the kind of thing that we're going to get with command line arguments. So let me just, oh wow, there's no space for my face with this meme here. I'm gonna shrink myself and put myself down here in the meme for fun. I've used this meme a bit because I really love this one, because like this American chopper argument meme always makes me laugh, and this one's like so meta for me because it's a meme with an argument in it, and it's about arguments. So I love it. Anyway, what's everyone saying there? Oh my god, Abraham's here. Hi. How did you get in here? Anyway, how's it going? Yeah. So as Shrey's saying, CP is not really technically a program, but we can treat it a little bit like one. Okay. So in order to accept arguments, our main, as in the first thing that our program runs, needs to actually have some inputs. So normally we were doing int main void. So we were always putting a void in these brackets here saying that we don't take any inputs. Now that we are taking inputs, we put this very, very specific, it's always going to be the same, two input parameters here. So one of them is called argc, and the other one is argv with a whole bunch of stuff on it. So one's just an integer, and the other is a character pointer, and there's the name array. So it's an array of character pointers. So if you want to think about it, a character pointer could be the address of a character, which can also be the start of a string. So that's how this is actually going to work, where it's an array of character pointers, which is an array of strings. So it's like a two-dimensional array of characters, or you can even think of it as a single-dimensional array of strings, if you consider the string to be, you know, an entire object on its own, which it isn't really. It's, you know, it's made up of pieces of memory, but it is kind of one block of memory. So we can think of it, of this character pointer argv array, we can think of this as just a series of words, of separate words. And when we when we actually run something like this, this will be the first element, second element, third element, fourth element, fifth element in that array. Actually, sorry. Everything that gets typed in the command line, so this is actually the first element. It will always have the name of your program, and then all of these, separated by spaces, will be the elements that are in this array. So inside our main, we actually start off with two variables already created. argc is the argument count. That's how many things that were typed in the command line. So this is always going to be one or more, because you can't run a program without at least saying the name of the program. And then we have an array, which is all of the words that were typed in on the command line when this program ran. So everything that made this program run. So I have an example program here. Let me just hop over to it, because like looking at codes on slides is okay, but looking at code in person is a little bit better. So this program is a demo of getting into arguments on the internet. So what it basically does is, it doesn't matter what you say, you will put some arguments in to the command line, and no matter what you say, the program will always say, well, actually, there's no such thing as whatever you said. So it doesn't matter what you say, this thing's going to argue against you. So it's an exact simulation of getting into arguments in stuff like Facebook comments and other places on the internet. What are we saying there? Mark, analyzing humor is a bit like dissecting a frog. You learn how it works, but you end up with a dead frog. I think that's potentially a comment on me picking apart my own meme and saying everything. So Peter's asking, is argv a pointer? Yes. So it's like this. Okay, argv. Actually, no. Argv is not a pointer. So this is a character pointer type. This is a variable which is an array. So it's an array of character pointers. That's what argv is. So when you consider an array of integers, if this was an array of integers, for example, you'd have this is the type, this is the variable name, and this makes it into an array of these variables. So this is the type, this is the variable name, and it becomes an array of these. So it's a series of character pointers, which means that if we were to use it, each one of those would give us access to a string if we wanted to, which is what we're going to do here. Actually, someone was asking me about fputs, fgets or fputs, so we're actually going to use fputs here. So, I mean, I'm not going to go through this code that much, but I'm going to at least run this once to show you. So let's compile this one. I think it was called arguments. Arguments, and I'll just call it argument. Make sure that compiles. Yes, it did compile. That's good. So in this code here, we have the number of arguments, and then we also have a list of strings, basically an array of strings here, which means if we were to loop through here, actually I'm just going to grab this, put this here so that my while loop here is really obvious. I'm going to start at 1, loop through until I is argc, add 1 each time, and for each of those I'm going to fputs. Fputs is going to dump the entire string to my standard output, which is right here. Standard output is the text that gets written to the terminal. So fputs is going to grab the text from this string and put it into the standard output. So the first element of argv is always the name of the program. So that's why argv0 is up here. So this program says that there's no such thing as, and then it'll type in everything else that I've got here. So let's just see this happening. So I'm going to say argument chicken is very cute. And this says, well, actually, argument, so that was the first element in the list, in the array. So we consider now we have this array. Each one of these words separated by spaces is a string in the array of strings. So that is argv. Argv is an array of strings. Oops. Here it says argument says there's no such thing as, and then it just repeats everything else that I typed in there. So obviously they're wrong. And so we need to continue arguing with them on the internet until they relent. Don't necessarily do that. Just getting into random internet arguments is not very good for your health. So what we're actually showing here, though, is the fact that we can now access the stuff that was typed in on the line that ran the program, and then each of those words goes into this array of strings here. So it can be a bit confusing because this is like, oh my god, too many symbols at once, but it's just an array of strings, which means we can loop through the array by changing I, like so, and then we access a single element of the array as a string, and we can print it out as a string. So fputs is going to do that. I could also, if I'd wanted to, done something like this, %s with a space, I guess, afterwards. This would have done much the same thing as the fputs there. I just wanted to use this because these are new, and it'd be nice to just kind of see how these things work. So printf will definitely print to the standard output. Fputs is able to actually print to other things as well. I haven't shown you what any of those other things are, but some of the possibilities that I could put here are files. So I could write to a file instead of just to the standard output here. I could also even write to a network connection so that the text that I was putting here would actually be sent to another part of the world instead. Literally how we would have an internet argument, you know, that kind of thing. So so I'm going to use fputs there because this is the kind of thing that it's handy to know about, because we could potentially be using these a lot more than printf. So oh no, people are quoting internet arguments there. So where we're saying if we want to get the value inside the argvi, we still need to use star argvi to access the value in it. It depends on how you're treating it, right? So if we wanted to get a single character, then yeah, we could do that. So this would be a pointer, and then if I wanted to get the first character, then I could do that. I think we would have to do this, and then we would say this is that address, this is the letter in that. However, if I want to treat this like an entire string, in the same way that I would treat an entire array, because the array is a memory address like a pointer, if I wanted to output the entire array at once, like strings are the only ones that can actually do this, I can give the entire string to fputs, and giving the entire string to fputs will mean the fputs will read all of the characters until it hits the null terminator. So that way, what I'm actually doing is I am actually giving a character pointer to fputs, and fputs will go, okay, I'm going to treat that as a series of characters until I find the null terminator. So it is kind of like we're giving a pointer rather than the actual letter. But you can also think of it, if you want to, as argv being an array of strings, in which case if I take a single element from an array of strings, it's a single string. And then it will be able to deal with the multiple letters in it because fputs knows how to do it. Okay. So that's the basics of how we actually grab this information. You will notice that this doesn't change. So no matter what we type in on the command line, I will always get a series of strings. So whether they're single letter strings or not, whether they're multiple letter strings that are full of numbers that maybe you think we should use as numbers, they're still always going to be given to the program in string variables, basically. So we need to grab these string variables and maybe make use of them. So we're always getting strings, but what if we wanted to do something like here with the numbers 1, 2, 3, and we want to say, okay, we want to process them as numbers. So in our program, if we want numbers, we want things to be of an integer type or a double type, and then we know we can use them as numbers, as opposed to a string type. If something is an array of characters, it's very much harder to use it as a number. So if we wanted to use a series of digits as a number, we would have to go through and access each one of those and say, okay, this number now is, you know, the lowest number, well, the one to the furthest right times by 1, the next one along times by 10, add them together, next one along times by 100, add them together. It's a fiddly process to actually turn that into a number that we can use if we only have characters. But luckily, standard library has, I think the standard library has 4 or 5 different functions that can convert a string to an integer. Here's one of them that we're going to use. It's a reasonably good one. There are others, so you will see others that you can use that will convert strings to integers. I think the reason why we use this one is it's reasonably safer, because I think it can check a few things. I can't remember exactly. I remember we had a big discussion about the different ones we could use, and we settled on this one, but I can't remember the exact flow of the argument we had about how we got here. But string to L, which is actually a shortening of string to long integer, from the standard library is able to convert a string of digits into a number. So let's have a look at this. Now what we can do is, if we have this code here is going to add together, I'm going to hop over here to look at it, is going to add together all of the numbers that are given to a given as command line arguments. So the first thing it's going to do is it's going to start at 1, because the first command line argument is always going to be the name of the program. So the name of the program is not relevant in this particular one, so I'm going to start at 1 instead of 0 when I'm going through the strings in argv. And what this is going to do is it's basically going to say, I've got a total, and I'm going to add the result of StrengthAlong for each string that gets put in as my command line arguments, and they're all going to add together to the total, and I'm going to print out what the total is. Let's have a quick look at what is in this StrengthAlong. Not super important, because this is one of those functions that you're potentially going to use, and you're not necessarily going to need to know all the nitty-gritty to be able to use this. So the first argument is obviously going to be the string, and if you want to, my text just disappeared. Let me just clear this so I can show you exactly what I'm typing in here. I can use the manual for StrengthAlong and see what information this thing is going to need to be able to run. So it's going to need a string, and it also has a pointer and a base. We are not going to worry about the pointer at this point, because as you can see, there's 2 of them there, so it's a bit fiddly. So what we're going to do is that pointer we're going to have is null all the time. That pointer is able to, for us, it's able to actually aim back at the string, but we're not going to use it, so we won't be worried about that one. So we're going to give a null pointer always for the second input. Sorry, second input's up here. But the first input and the third input are important, where the first input is the string itself that's going to be converted. So that's just going to be, I read in these strings from the command line. I'm hoping that they have numbers in them, so this is the thing that I want to convert. And then we have the base. So I've talked a little bit, but not really super explicitly about what number basing systems are. So in this course, we have definitely used the decimal base system, which is the base 10 numbering system. We use this base 10 numbering system naturally as humans. The funny reason of why we use a base 10 numbering system is our initial maths as we were developing was based on the number of things that we could count at one time. So we said that's a full quantity, and then we go up to the next 10 also. So our base system, that's why there's 10 digits. The computer is different. The computer, it does not have these 10 physical digits. I mean, sure, there's somewhere out there there's a computer that has 10 fingers, and I'm sure it's grotesque. Or just a robot, right? Some robots have fingers. But we have been using a base 2 system a lot of the time with computers, and that's the binary system. So it only has a 0 or a 1. Most of our programming hasn't really touched on binary or used it that much. The other one which we've seen, but we haven't talked about that much, we've been using it a lot without knowing that we've been using it, is the hexadecimal system, which is a 16 base system. So StrengthAlong is able to change different systems depending on what you tell it the number is. So if I'm going to input a number that is a binary number, so it's made up only of zeros and ones, and is meant to be binary, then I'd use a base 2 here to say this is a base 2 system. If I was going to input memory addresses, for example, memory addresses are usually formatted as hexadecimal numbers. I would put a base 16 in here. If I'm using normal decimal human readable numbers, then this is a 10. So the things that we would do with StrengthAlong is, like, we know StrengthAlong is here, we're going to put a string in, and we're going to say this is the basing system that we're going to convert that string into a number via. So if it's a number that's just of the digits 1 through to or 0 through to 9, it's a base 10 system. But if it's got the digits 0 through to 9 and the letters A, B, C, D, E, F, that's a hexadecimal system, and so that would change this. So simple thing we're doing here is we're taking in numbers in the command line, we're using this function to convert those numbers into integers, and then we're adding those to a total. So we've got a total here that starts at 0, and then we're going to add each number that we type in the command line, starting from the second thing on the command line, and that means that we're going to ignore the name of the program, which is also in this array. So note how I said before, the first element in this array is always the name of the program, the command that actually ran it, and then everything after that is whatever you typed in the command line. So let's compile this and have a look at it working. I'm going to clear that. Adder. So if I do that, I think that's going to do nothing yet because there were no numbers there. But if I do adder 1 and 1, what's going to happen when I do that is argv is going to be an array with 3 elements in it. First element is going to be this word, /adder. Second element is going to be this word, because it's still a word at this point, which has the digit 1 as a character, and then this other digit 1 as a character. So this while loop is going to skip the first word, which is /adder, which is good because we didn't want to use that one as a number. And then it's going to go to index 1, which is this 1 here, and it's going to say, okay, convert the string 1 into a base 10 number, so it turns into the integer 1, gets added to the total, and the other one does as well. And we can do this with more things. So we could do 1, 2, 3, large number, and it will be able to grab each of those words and convert them into an integer that we can use. People are asking questions. Ah, Dean's here. Dean's answering a lot of questions there, so that's good. I'm going to let Dean and Shrey answer those questions. There's a lot of questions there, and I could get bogged down answering all of them. They're good questions as well. So I think Yiji's talking about the actual type of the arguments, and so I hope you get a good answer for that here, because this is a very specific way of looking at types. Oh, Catherine's saying, what happens if we type in a letter or a word here? Let's try that. So A, B, C. Total is 0. So what I think has happened in here, I don't know for certain, but StrengthAlong has either returned 0 there to say that it couldn't convert it, or it has refused to convert it. But either way, what's happened is total has not changed from 0. So either it's added 0 multiple times with the ABC, or it returns 0 if it doesn't find a number. I think that would be another thing to check. We could check on the man page because it might actually say that. I probably don't need to do this, but anyway. Converts initial part of the string. Must be between 2 and 3, all the special value. No. Oh, that's the base can be between 2 and 36. If there were no digits at all, StrengthAlong stores the original value of the pointer and end pointer. That's the pointer we're not using at the moment, and returns 0. So if it doesn't find any letters, if it doesn't find any numbers, it will return 0. Peter's saying, do we need to do something different for negative numbers? Let's have a look. 1, -1, -100. We do not need to do anything different for negative numbers. So StrengthAlong is able to detect that this is a valid number. So it's able to say that this negative is part of a valid number, so we are going to use it as a valid number. Matthew's asking a slightly different question there, so it's not necessarily about this, but it's about this part here. With something like DCC, why do some arguments have a special symbol like this? The way this works is actually quite complicated, is that DCC can take in different inputs, but it's not specific about the order of the inputs. At some point, it's going to want C files, and it can have more than one C file. But if it sees a certain symbol, like a dash O, and there are other dashes, so I don't know which ones DCC has, but it also has the leak check and stuff like that. Every time it sees a symbol with a dash, it's going to say, okay, the one that comes directly after this has a specific use. So when it sees this combo, it says usually everything that I take as input is a C file. So anything that doesn't have any of these dashes in front of it is a C file. But this is not a C file. So this is us saying, okay, the next thing I'm going to tell you is the output name of the program. So these are special symbols where if I was writing DCC as a program, I'd say, okay, everything in this array, you'd have to go through the array in order, and you say everything in this array is a C file, unless I see a dash something, in which case I would go through some if statements to decide which thing it was, and then say, okay, the next word after that is going to have a particular meaning. So this is saying, store this string as the name of the output program that's going to be created. So it's a bit like that. Yeah. Yeah, so Matthew, it's like a command line keyword in a sense. Like, you'd see this and you go, oh, that means I'm going to react differently to the things that come afterwards. So that's some of the basics of command line arguments. The more we fiddle around with these things, the more we'll see, okay, there's certain things that we may want to give in the command line. And it's also technically possible to never use command line, because if you wanted to, you could just say, don't take anything on the command line, and then take these three numbers as the first scanf inputs of the program. So that's why I'm just sort of throwing this in here. It's not a super important thing that you need to know, but it's kind of handy because it's how a lot of programs run, and it's how like just a whole lot of the operations in a terminal run. Is they say, you say what your command is, and then you say a bunch of other stuff. So it's good to know about. But if we wanted to, we can totally get away with writing programs that never use the command line. I mean, I'm saying that in a practical sense. In terms of like learning the course, we're obviously going to get you to do some of these so that you learn about them. We don't want it to be like something that we just mention and then disappears. I don't think there's anything that I teach in this course that's like that, apart from maybe the memes. But the memes are there to like try to get your attention onto things. Okay, so I think that's everything that I wanted to talk about command lines. It is, yes, good. I'm in sync with my slides for once. So the command line stuff is stuff that can come in handy. The next thing I'm going to teach you is something that is potentially way more important than the command line argument stuff, and this is where we're going to start doing some pretty cool stuff with structs. So this is where we're going to make a big brain leap at this point, and we're going to start building together a whole lot of the bits and pieces that we've used before. So let me introduce to you a new kind of struct. This struct is called a node. You will not forget this because you will see this again and again and again. The idea of a node is the idea of a piece of memory in your computer that contains some information. We'll usually be storing some information in the node, and the node will be connected to other things. So the way that we're going to connect nodes to other things is pointers. And so at this point, this is a really interesting thing because we have not done this before. We have a node, a struct node. Inside the struct node is a pointer to a struct node, which means that this structure always contains a pointer to another of itself. It's not always another of itself, because you can have a null pointer, but if this pointer is aimed at anything, it'll be another variable of the same type. So what we can actually do with this is we can say, here's a node, and it has a pointer to another node, so here's another node, and then it has a pointer and it links to another node. And you can already see now how I can start chaining together these things by saying, look at the pointer in this, it takes you to another one. Look at the pointer in this, it takes you to another one. And then we can start actually going through this chain, and then we can put together a collection of things that are just chained together by the information inside them. So each one knows where the next one is. It's nearly like a scavenger hunt or a treasure hunt or something, where you go to a location, you find a little piece of treasure, and some of it is the treasure, the data, but some of the other stuff is just like, here's where the next one is. Here's the address of the next one. You go, oh, okay. And you go to the next one. It's somewhere else in memory. And you go there and you go, okay, there's some data there, but there's also the address of where the next one is. It ends up looking like this. So, in our memory, obviously not to scale, these are just the diagrams I like to use. In order to find the first node, we're probably going to need a pointer. Either that, or we know exactly where this node is because we created it. We're going to create all of these nodes. We're actually going to do some of this today. So we have the node, and inside the node, there's actually not usually this much extra memory around it, but obviously, as I said, not to scale, so it's okay. There's a pointer to another node and some information. So this pointer to the other node, we can follow this pointer, and it takes us to this node. And this node says, look, I know where there's another node, and I also know that there's some data here. But you can follow this to the next node, you can read this data, and eventually, because this isn't necessarily going to be an infinite linked list of nodes. This is a linked list, by the way, so this is like, I've mentioned this from the very beginning because it's one of the exam hurdles in this course is to at least be able to use one of these. It's not even necessarily be able to build one of these from scratch, it's just to be able to use it is the hurdle. But we are going to teach you how to build them, how to manipulate them, and things like that. And the whole second assignment is based on this data structure. I mean, it's more than just this, but there's heaps of linked lists in it because this is one of the things that we know that you're going to need to know to sometime in the future if you're going to continue with computing. So at some point, the next pointer is going to be a null pointer that says, okay, there's no node after me. But this kind of setup now is this thing where we can say, oh, I can have a whole series of these little data packets. I shouldn't use the word packets. Packets is a networking thing. So we have these little pieces of data, and I have a pointer that says there's another piece of data somewhere. And so this piece of data is here, and this also has a pointer to the next one. So what we have now is something that you could consider to be like a super convoluted array. Because we could have just had an array where all these pieces of memory was next to each other. But instead of these pieces of memory being next to each other, these can be anywhere in memory. So these aren't necessarily going to be in this nice neat line like this. They're in a nice neat line so I can talk to you about it theoretically and you can understand it the first time you see it. But in reality, these nodes are just like off in different parts of our memory. But we don't mind where they are in memory because we've got pointers. So this pointer is always going to tell me where this one is no matter where it is. So that's the structure we're going to be using. And it's all based on this simple concept here, is that we can develop is the right word? Not really. We can declare, that's the technical term, right? A structure that has a pointer to its own type. So this is kind of cool because usually you can't use something until it already exists. So we're actually using it when it only partially exists. But we can actually have pointers to things that only partially exist. That's okay, because the pointer is just a memory address, remember. So I'm storing a memory address of another one of these inside each one of these. Allows me to chain these things together. So it allows me to say, I can have these four, let's call them integers for the moment, these four integers together in an ordered list, but not necessarily right next to each other in memory. In an array, they'll always be right next to each other in memory, and they'll work in a specific way. In a linked list, they're not necessarily next to each other, so they just have pointers to each other, and they can be anywhere in memory. The benefits to that is it's actually really easy to squeeze another node in between these two. If I wanted to remove this node completely, I could remove it and just have this pointer skip over it and go to this one. So I could just change the location that this pointer is storing from this node to this node, and then suddenly I'd have a working list here. We're going to do all of that stuff eventually. Not right now, though. Not today. Today we're going to start joining some of these things together, but we're going to start with just like, okay, how does this even work first? And then we're going to build up more and more about it. So Steve is saying, can you connect the last one to the first one to make a circle, and is there any point to that? Well, actually there is. You can do some really cool stuff with that. So if I connected this one back to the first one, we could create a thing that, one of the things that we use sometimes is a thing called a ring buffer, where you could store all of the stuff that someone's typing in, and you're going to go through, so like you're going to type letters in, and then it loops back around and stuff, but like what's going to happen is something's going to read all the letters that are typed in, so they would just be following just behind. and then reading all the letters that's typed in. You can go, so you can have temporary storage for something that's a limited amount, and then you won't store any more than that. I don't want to go into too much detail, but yeah, you could do a circular linked list like that. We're not going to be doing any of those in the course. I think we have like maybe some challenges where you could use them, but generally we're not going to. We're going to keep it simple so you can understand the structure first. Lang's asking, can't we just use multiple identifier data pointer arrays, then link them together like that instead of using structs? Liang, we could if we wanted to, but remember that arrays always have the same elements in them. So if I was going to say that one of the elements in the array was a pointer, it would mean that everything else in the array would be a type pointer. It would be the same type. So it would be much harder for me to store in my structure something complex. So for example, those kind of airbender things that I was, well, not airbender, like element bender things that I was talking about previously, if I want to store arrays of characters, integers and stuff like that, and a pointer, then I'd be better off using a struct, because I want to build that custom data structure. It is possible also, if you want to, is to have that custom data structure and put that into an array. But then it's an array, not a linked list, and the linked list actually has more flexibility than the array, which we will see. You've got to be patient with me. I'm going to go through the whole of linked lists and how to use them. So we're pretty much going to do one programming example that starts today, and it won't finish until the end of next week. We're going to go all the way through. We're going to do heaps and heaps of code, because linked lists have a lot going on. So this is the linked list, and because I've taught you about arrays and you know about arrays, I think it's important for me to show you the difference between the linked list and the array. Where are we? I'm seeing what people are saying there in case I need to say anything, but I think Dean is answering most of the questions. Peter's saying 3D linked lists. Yes, they are possible. Let's not talk about that in COMP1511. Let's get a one-dimensional linked list working first. We are going to see two-dimensional linked lists, or even two-dimensional data structures, because they're really easy. Because I can put an array inside the struct of a linked list, and I've technically got a two-dimensional data structure already. Because the linked list can be there, and the arrays just kind of hang off each of those nodes. It's not too hard, you know. Catherine's saying, going to have to watch this lecture again. Yeah, there's a lot going on here. But don't worry too much, stick with it. I'm going to work through it, and we're going to actually build up the code in bits and pieces. Okay, so an array is a single block of memory. It's a single block of memory broken up into multiple variables, right? The linked list is not a single block of memory. It's all these individual pieces of memory. Each node is in its own piece of memory somewhere, which means we can easily shuffle things around. So the only thing I need to do to shuffle things around in a linked list is just change where the pointers are aiming. So I could just completely change the order of a linked list by just changing a bunch of the pointers in it to aim at different things. I have to be careful that I don't lose any of the linked lists when I do that, because the only way that we can keep track of, say, these elements in the list is to know that we know where this pointer is. So if I have this pointer aiming at this element, then I know that I can always find this element. If I was to delete this pointer from inside this node, then these two, I can't access them because I don't know where they are. The only thing that knew where they were was this pointer here. So I've got to be careful. There's the potential here to lose a whole lot of memory if I was to just delete this node, for example. If I just delete this node without thinking about it, then I would lose this next pointer and I would never know where this one is, and then I'd never know where this one is and never know where this one is. So the structure itself, if we start screwing around with it, is fragile, but it's very, very flexible because I can easily put nodes in between other nodes. I do not have a fixed length. So I don't have to do the things I'd have to do with arrays. Like sometimes with arrays, I've got to make something really, really big in case the number of things I want to store gets up to that size. A linked list, I don't have to do that. I can make the linked list exactly the size it needs to be, and if I need it to be longer, I just add nodes onto the end. So there's some really nice flexibility there. So the length is not fixed. I don't need to limit myself to a maximum length or anything like that. And as I was saying before, I can add or remove items anywhere in the list. Using an array to do that is super finicky and sometimes infeasible. If I tried to insert an element in, say, the second position in an array, I would leave the first one as it is, and then I would say what was in the second, copy it into the third, what was in the third, copy it into the fourth, copy them and just shuffle them all along, and then put this element in here. So it's really, really fiddly to do that with an array. So the linked list, it's really easy. You just say, okay, the pointer goes to the new thing, and then the pointer links up. And so you just keep the chain, and you're fine. So long as we maintain this chain of pointers from the pointer to the first node, next, 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 all the way through until the final node has next equal to null, then we've got our linked list all nice and connected. Okay. Yuji saying the day of struct inside struct eventually came. I told you I was going to do that. It sort of works though, because it is easier to put structs inside structs than it is to have something like pointers to pointers. Pointers to pointers is much more confusing for the human brain. But for me to say, I have a struct that's a node, the key part of the struct node is that it has a pointer to another node, and then everything in here I can do what I want. So I can put arrays in here, I could put an entire freefall map inside each of these nodes. And what I could do then is say, okay, you've got a linked list of freefall maps. This is your level structure for the game. You have to do this one first, and then you follow the next pointer to find the map for the next one. Then you have to complete that map, and then you follow the next pointer to the next one to complete that map. So I could actually use that as a structure for like a level-based freefall that goes through multiple maps. Obviously that was not part of assignment 1 because you need a lot more knowledge before you could do that in assignment 1. But that's something cool that you could do now if you wanted to. If you wanted freefall, every time you finish a level to maybe go on to the next level, you could actually store the levels in a linked list data structure. I should probably teach you about the linked list first before we do that. Okay, so these are some of the reasons why we have linked lists. They can do more than arrays, but the cost is that they're a little bit more fiddly and a little bit harder to understand. So they do have an advantage over arrays in the beginning, like that. When you get into much more complex linked lists, then the advantages get much bigger as well. So the first step is just like an array but a little bit better. But later on into the future years of using these things, you will then be doing really fantastical complex things with these things, and they're really cool. Okay, so let's think about putting together a really, really simple Steve. Okay, Steve said, wait a minute. The nodes of a graph are basically the same, but each node contains an array of node pointers, because each node can point to multiple things. Yeah. So that's the complex thing that I wasn't going to mention, but since you mentioned it, I might as well. Yeah, so if we had multiple of these pointers, we could then connect up multiple nodes into a network of nodes rather than a list of them. We're not gonna talk about that though. We're gonna learn the basics, get the basics correct. One must learn how to connect 2 Lego blocks together before one starts building the 3,000 piece Lego Millennium Falcon, because like it's a bit much to jump to the hardest thing. So we're at like basic bricks here, and then we understand how they work, and then we'll start getting more complicated. So simplest thing we have, every node has a pointer to a node, and it also has something that it carries, which is going to be some kind of information. So for the moment we're going to keep that simple and use something like an integer for that. And so here's a function that I've written, and I have this actually as demo code. I'm not going to go through this in great detail because we're actually going to write it again later in the demo in the second half of the lecture. But if I wanted to create a node, what I could do is I could say, ask the rest of my program to give me the contents of this node. So give me the next pointer that it should be, and give me the data that should be stored in it, and I will make this node for you. And so this isn't too hard. What I do is I make a pointer. I could have done this on one line actually. I allocate, so allocating memory, we've done this already. Allocating memory for a node, so I use the struct node as the size of the memory that I'm going to allocate, and I store that in this pointer here. So I'm just calling this n for now. If we want to, we can do this check. I probably won't even bother with this check. This check says malloc will return a null pointer if it wasn't able to allocate memory. However, if it wasn't able to allocate memory, we're probably going to get that killed message before we can even get to this code here. Well, this is trying to say, oh, it didn't allocate properly, program will exit. Usually if I try to allocate memory and there isn't any memory left, I probably won't even get to this point. So I might not even bother with this test when we're writing our code. So the thing, actually, you know what I'm going to do? Let me just delete that. It'll be much easier to read if I do this. Okay, I've just really shortened my example code here. I allocate the memory for a node, and I say the data in the node is whatever data it gave that I was given. The next pointer of the node is whatever next pointer I was given, and then I return that node, the pointer to that node, so that whatever function called create node to make this node for them now knows where that node is. So this is really simple. This is me just saying, you've got a struct. If you give me all of the information to make one of those, I will make one of those for you. So I allocate one node's worth of memory, I get a pointer to it, I put the information in that you gave me, and I just give you back the pointer. Reasonably simple piece of code here, but it is tying together a lot of the complex things that we've been working on, right? We have to be able to understand this simple bit of memory, we have to understand that a struct is something that's been declared earlier, like so, and it can be memory allocated because we can see what the size is, we can allocate memory for it. So we can grab a piece of memory on our computer and say, okay, this is for this node. Malloc will then give me back a pointer, so I can say, okay, I'm going to store that pointer in this one called n, and it has to be a pointer to a node, a struct node, because that's the size of the thing that we're creating. And then to go into that struct, because this is a pointer to a struct, I use the pointy connector, the arrow, and so I set its data to what I was given, set its next to what I was given. I don't know what these are yet. The way that this function is used will determine what these inputs are going to be. And then when I'm finished, I say, okay, here you go. I've packaged the node up for you. I have allocated the memory for it. I've put the information in. Here's the pointer, so you've got access to it. So this create node is reasonably simple. It's just gonna do that for us. Now, if we want to, we can build up a linked list by just calling this create node multiple times and using this pointer head. So one of the terminologies that we're going to use a lot when we're working with linked list is head is a pointer to the start of the list. So when I had this here pointed to the first node, we're now going to start calling this the head pointer all the time. So the head of the list and the tail of the list. It's like the linked list is a snake going through our memory. I've told you about that one, haven't I? The snake going through memory? I think I have. Yeah, so the head is at the start of the linked list, and the tail is all the rest of it that's going through. So what I can do is, my first one is create a node with a number 1 in it, and its next is null. And it is the head of the list. And then what I can do is I can create another node which has the number 2 in it, and its next will point at the head. So its next will actually point at this node that contains 1. And then once this is finished, we will say, okay, create node is going to give me a pointer to this number 2 node, and I'm going to say the head is equal to this. So what I've done is I've said now number 2 is now the head of the list. Let me show you what I mean by this series of creating nodes. So first thing I did was I created a node with a number 1 in it. Hello. And then its next was null. Then I created another node, which was the number 2. Oh, sorry. Let me just have a head pointer pointed here. So the first line of code was create the pointer called head and make that equal to the result of create node 1. So create node 1 has a next pointer aimed at null, and the head pointer is aimed at it. Then I created a second one, and it had a 2 in it. That's this line here. The right hand side of this line creates this node 2, but its next now is not pointed at null, its next is pointed at head. So its next here, if it's the same thing as head, it means it's pointed at the same object that the head is pointed at. Then head is equal to create node 2. Create node 2 is this node here. So what happens is head becomes equal to number 2. Which moves it to here. And now I've started building a linked list with multiple objects in it. When I create 3, it's going to do a similar thing. So let me just... I'm not going to go further than 3. I just wanted to draw this so that you can see it. So I create another node, and it stores the number 3 here, and its next pointer was pointed at head. Okay, so next pointer being pointed at head means that it takes the head pointer's address and says, okay, I'm going to point the same thing that you're pointing at, because head's an address, and the 3's next is going to be pointed here, and then the create node of 3 is going to tell us what its address is, and we're going to store its address here in head. So we're going to move the head pointer to number 3 here. See how accurate my erasing is there. Oops. I want that to be the color of that pointer. There. And so what we do is every step of the way when we've added something, we've been able to put more elements into this list, and we're actually inserting these elements at the start of the list because the head pointer keeps moving to the new element, but each new element says, okay, whatever used to be at the start of the list is what I point to as my next. And so that way we're always getting this chain of elements together, and we can build a really, really simple linked list like that, where all we're doing is inserting at the start of the list. So it goes like this. And so by the end of this, my list is going to be 5, then 4, then, sorry, from the way you're looking, 5, then 4, then 3, then 2, then 1, in that order, because the last one is in the head. So what this is doing is just adding new elements to the list, and each new element becomes the new head of the list, and then it points to the previous head of the list as its tail. So it's interesting to think about the order that these things are going to happen, because this create node is going to happen first. It's going to point at the old head, and then it's going to replace that old head with its own location. Right. Oh, Alex asking whether node is a variable name or a C keyword or anything. It is actually our struct name. So node is not a reserved keyword. It's something that we often use, but we won't always use node. Sometimes we'll use something else. Like later today, I'm going to use I'm going to do players in a game, so it's actually not going to be nodes at all. Okay, so, oh, here's a diagram, but I've just done the diagram in Paint. I think maybe it's easier to see it in Paint anyway. So this is that same kind of thing of 1 goes there, 2 gets added before it, and then the head moves to 2. It's probably better to just go through, if you need to, go back through what I did in Paint. It's going to be better than these, I think. Okay, so let's take a break. And here's the big brain thing I was talking about, right? Because what we're doing now with linked lists is we're tying together what is nearly a month's worth of work leading up to this. So I first introduced pointers probably nearly a month ago, and the whole idea of memory addresses and us being able to store memory addresses in pointers. Then we looked at structs, and so we thought, okay, now we can build custom variables made up of other variable types. This includes pointers. Where am I covering the meme? You know what? I'm gonna be the big brain. Oh yeah, I'm gonna put myself down here in the big brain. So yeah, so we had structs, and structs can contain pointers. And the next thing that we looked at today was if we have structs that can point to their own type, that means we can chain them together. Um, and then obviously we're going to be using our memory allocation to make sure that whenever we create one of these, it doesn't just last as long as the curly brackets that it's in, we want it to last longer. So for example, here, every time we call create node, we want this thing to last, because otherwise, the node, if we didn't memory allocate it, would just disappear at the end of this. So there's no point in having a function to create it in that case. But because we're memory allocating, it lasts beyond the scope of this function. So the scope of this function is limited by its curly brackets. But memory allocation says, I can give you a piece of memory that's outside of these curly brackets, and you can use it. So this allows us to build this list, like so. Okay, let's take a break. When we come back, we're going to start building up an example that we're going to do over this lecture and the next 2 lectures. So there's going to be heaps of code. I'm going to talk about how we build linked lists, how we use them, and things like that. So let's go on break. It is Chicken's very hungry, as you can see. Oh, you can see her ear on the screen there. She's basically just sitting right in front of me, just going, it's food time. It's food time, and I'm very hungry. Okay, so we'll take a break, we'll feed Chicken, then we'll come back and we'll start using these things. I'll be right back. And we're back with a little feeding time. Take a break, relax, maybe even have a bit of a snack if you want. Chicken's having a snack. Alrighty. I'm just gonna change the screen while I move the camera back. Alright, back to me again. Slightly less interesting. COMP1511 staff. I just work for chicken, you know. Okay, so I did see a lot of questions there. Ooh. Slide 14, I am missing a semicolon. Yes, I am. Oh, wait. Not there. There. This slide. Yep. I had the incorrect code there for a struct declaration. Structured declarations are a little bit weird because they're slightly different from functions. Functions won't end in a semicolon, but structs kind of are like a single line thing, even though we will always be splitting them over multiple lines, and so they're considered to have a semicolon. Slide 11 as well. Yeah. Apologies about that. I'm not sure how these slides made it this far without those semicolons. Because I've used these, I've delivered this same lecture several times before with these slides. Anyway. So long as we're progressing and getting better, it's good. So thank you for the correction. That's really handy. Yeah. He's behind you! I don't think that one was an intentional mistake, because that one's a very silly mistake that doesn't teach anyone anything. You can always tell my intentional mistakes, because they will call it something like a compiler error that's interesting to solve, not just like a missed semicolon in something like that. Okay. So an interesting thing now that we're getting is that linked lists do not have indexes the way that an array has. So an array, it's really easy to loop through because you just use a number and you just count upwards, and as you count upwards you can access different elements of the array. So that's just putting the number in the square brackets, right? But a linked list doesn't do that. A linked list just sort of exists in space, and you need to follow the pointers through the linked list. So what we're going to do when we loop through a linked list is we're going to use a while loop, but instead of instead of being able to access each individual element, we're going to use pointers. So we're going to have a pointer to the first element, so we're going to assume here that this is a pointer to the first element of the list. So it's interesting because the pointer to the first element is a pointer to one node, but it's also kind of in an implied way, it's not just a pointer to the first node, it's a pointer to the first node that then says, okay, the rest of them are going to chain off this. So if you have the pointer to the first node, you should be able to access all the others. So what we're going to be doing, this is a really simple one that's just going to print out the data in each of the nodes. So this is going to print out the number that's in the node, and then a new line. And then when we've finished reading the data, our pointer goes to the address of the next node in the list. So a pointer called n becomes, look at the current thing it's aimed at, and then it's next. So this is me saying, here, start with a pointer that is usually a copy of the head, and we go, okay, first node, we read our data and we write it out. And then we say, okay, we read the next instead of the data, which gives us this address, the address of this object. And then we can move the pointer to this by saying the pointer that we're calling n used to be aimed at this node, now is aimed at this node because it's copied the value of the next. So we go, okay, what's in our current node? What's the next pointer of our current node? That is the location we want to go to next. So we say, okay, we no longer want to be pointed at the node we're pointing at. Change n to point at the next. So this is us editing the value of the pointer itself. And so remember, the pointer, the value of the pointer itself is the memory address, the location it's aimed at. So if I change the value of a pointer, it changes where it's aiming. So originally it was aimed at this node, but I say copy this next pointer, and this next pointer was pointed at this address, so it changes where the node is. The node ends up here. Sorry, the pointer ends up here. And then eventually, as I loop through the list, I'm going to do n next. So if n was here at this point, n next is null, then I'll get a copy of null, and I get this condition for the while loop. So while n is not null, keep going to the next node. And eventually you go through all the nodes and you get to the end, and then you change n to null by following this next pointer that points at null. And then when you hit there, that's when you stop looping, because there's no more data to look at. So the while loop for a linked list is moving a pointer between the objects of the list, one after the other. And it's really similar in the way it functions to the iterating the number I from 0 upwards. But because there's no numbers this time, you are moving between the objects one at a time, but you're using the fact that they each know where to go next. So this is like the example I was saying before of like using like a scavenger hunt or something like that, where you go, okay, we know where the next one is from what we can see in this one. So this one tells us where the next one is, so we can move our pointer. This one tells us where the next one is, we move our pointer. This one doesn't have any information, so we know that there are no more elements in the list. And so that's how we would loop through a linked list. People are saying the brain's hurting. Yes. Don't worry. I do understand that this is the point at which people's brains hurt the most, because we are connecting a bunch of these things together. So Jed's asking, what is next? Next is a pointer. So next is an address of another node. So remember, the node struct itself has a pointer to a node type and some information. So if it's a pointer to a node type, then the thing at the other end of the pointer is going to be another node. So if we copy next is the address of this object, and then we would get this pointer here. And if we copy this next, this one happens to be null, then we'll get a null pointer. So we're going to keep moving along until we get to a null pointer. Oh, Reese has not gone to any tutor labs. Oh, that's really sad. You know, they're actually kind of fun as well as like being educational. I don't know. Well, sorry, you work and stuff, so like you've got pressures on you that are stopping you from going. Hopefully, you've at least been able to watch some of the recordings when you've had some spare time. And Terry's saying that, yeah, Tutors and Labs will carry a lot of people if you don't understand the content. I mean, I'm under no, like, I'm not under the misconception that my lectures are enough. As much as I put a lot of effort into my lectures and things, I know that 4 hours a week is not enough to understand this stuff, which is why the Tutors and Labs exist. If you just listen to me, there's a chance that you would get stuff, but you really need to do it as well to know that you can do it. So, personally, I think everything ought to be linked together. Jed's saying, do we need to declare the next pointer? Let's go back here. When we create a node, we have the next pointer. So when we memory allocate the node, the next pointer will exist. So n next will exist, and we set it to whatever we were told to set it to when we created the node. So for example here, we keep setting it to the head, which was this example here where the head was moving between these nodes, and each one links to the one that had been the head previously. So when we say we're declaring those pointers, we kind of are in this malloc. So when we malloc a struct, it gives us all of memory for all of the fields inside the struct. That could be considered to be declaring. It's not exactly the same, but it could be considered to be declaring every variable inside the struct. None of them will have any values until you set them. That's why create node makes sure to set both of the values inside that particular node. Yeah, Dean totally knows this. That like this point of the course is usually where anyone who's programmed before finds, okay, this is where it significantly jumps from basic programming into programming with memory management and things, and this is where we turn from people who can code, just sort of generic programming. This is where the computer science comes in, because being able to build these weird data structures is this sort of next level of how do you design the architecture of your code. So we're going to give you all the design of this, but in the future you might be designing things that have all this kind of moving parts in it and stuff. And so this is like, it's like, yes, I'm teaching you one technical thing about how to work with a data structure, but we're also teaching it in a way that shows you how we design it from scratch. So from these fundamental pieces over the last month or so, building up into this and then joining things together. Okay, so yeah, what Yuji's saying, the commands are easy, but it's the logic of what's going on. So this is why you'll note that I've crossed over into this world of drawing lots of stuff now, because I know that this is the point where the theoretical understanding of what's going on is potentially just as important as the being able to write code. In fact, it's really hard to understand the code if you don't understand the theory, because if you look at this thing, it's really simple, there's not much in it. But just this one line is complicated, right? What I'm saying is, I have a pointer n that's aimed at a node. I am then saying n will become n next, which is me saying take the pointer that's in the current node that's aimed at something else and make a copy of it my current pointer that I'm using, which moves the pointer from one node to the next. So if you can think about it in the abstract way and say this is moving the pointer to its next, that's okay, but you also want to know that what this is doing is it's taking the memory address that's stored in the next node of the node I'm looking at, and then copy that memory address over the pointer that I'm using to look at n, and that then aims n at the new node. So it's a little bit full on, right? What's going on there? But if we can look at it in two different ways, like one's from the hardcore code sense, and the other is from the abstract idea of these blobs in space that we can point arrows at. Sometimes that helps in our understanding. I just saw Dean say practice is the only antidote. Yes. Understanding this stuff comes with time. The more times you do it, the better you'll understand it. And that's why we've got a whole assignment using these things. Okay. Example. This is a big example, and it's gonna span multiple lectures, and it's a battle royale. So I don't know if anyone here plays Fortnite or PUBG or any of these games, which I think are one of the, it's not the newest genre, I guess, in games, but it's like one of the newest, biggest genre in games, is games where you put a whole bunch of people into a game, and then they get knocked out one way or the other. So the way the game works is like it has this big circle in space, and it shrinks it, and people fight each other, and so eventually everyone just gets forced together into this pack to have to fight each other, or they get into these little skirmishes. Basically, people get knocked out one at a time until the end. And so what we're going to do is use a linked list to track the players that are in the game. The linked list is very well suited to this, because in a game like that, you don't know the order that people are going to be removed from the list. So someone could get removed from the start of the list, someone could get removed from somewhere in the middle of the list or the end of the list. You don't know, but the linked list is really good at just removing an element from somewhere in the list. So that's why we're using a linked list to store the information on the players in the game. And there's a few things we want to be able to do. Right, so we want to be able to print out all the players that are currently in the game. That's not too bad, because I've already shown that we could do that with some really, really simple code here. But that's just one of the functions. We need to also maintain this list. We need to build this list by adding players to the game. So when the game starts, we'll add a bunch of players to the game. As the game goes on, we're going to remove players, and we're going to be able to print out the list of who's currently still in the game. So this is the bit here that as players get knocked out of the round, we want to be able to remove them from the list. The other thing we might want to do is we might want to be able to control the order of the list. So as a simple example, we might want to have the list go in alphabetical order. If we want the list to go in alphabetical order, what we would want to do at the start of the game when we're adding players to the game is to only ever insert things in alphabetical order into the list. We're going to be doing all of these things. It's going to take a lot longer than the half hour I have left here. This is why this example is split over multiple days. But what we're going to do today is at least we're going to start by adding players to the game and potentially printing out. We'll see how the time goes. Liang wants me to do the dance for you. COMP1511. COMP1511 is not a battle royale. We're not going to knock out 99% of you and only have one left. Wait. There you go. Alright. I can't do it at full speed. That's as close as I'm going to get to a to a Fortnite dance. Jed was asking if this is assignment 2. It's not directly assignment 2, but everything we're doing in this example will be really, really connected to what's in assignment 2. Okay, so let's get into this and see what we're going to do. So, what are our names going to look like? We're going to start with a really, really simple name. Sorry, we're a node, not names. I jumped ahead. So the node is just going to contain a name. So we're going to have the different players in the game, but we're not too worried about their stats or anything like this because we're just maintaining a list of who's in the game and who isn't. So we're going to have a name. So what I'm doing here is I'm going to say, okay, there's a character array in here and there's a next pointer. So the basic structure of the linked list node is the same. Contains some information. Previously we used an integer, this time we're using a string. Not hugely different because structs can contain different types. Everyone's laughing because I did the flossing dance. I can't remember, what's the default dance? Is that one? I can't remember which one is it. Anyway, we're going to go on before I embarrass myself by doing more Fortnite. I don't even play Fortnite, but I know a lot of the dances just because like you end up learning the dances because you just see them everywhere. Okay, so this is a simple linked list node structure. The thing that makes it something that can be made into a linked list is the fact that it has a pointer to its own type, which means it can join to another node of its own type. It has some data that it's carrying. This time it's a name. This could even be multiple things if I want to. I could have a name. I could have, I don't know, what skin they're currently wearing, what hat they've bought or whatever. I don't know if do they hats in Fortnite? I don't even know. Team Fortress 2 used to have hats all the time. So I could have all this other information in here if I want to. The only thing that makes it necessarily a linked list is the fact that it has a next pointer, and then it can carry any amount of information that we want to. You can carry massive amounts of information in here if you want. I mean, for example, here, this max name length, I don't know how big that is, so it could be a large amount of memory. And then we'll have a create node function. So let's jump in. Yeah. Oh, I'm gonna do this myself. I realize in my slides I've got people who are no longer working on the course there, and it made me sad because they're my friends now who have moved on to other work. So let us. Okay, so I don't have anything else in there that I need to do. I do have code for the basic linked list demo, and that's in the lecture section on the website if you want to look at it there. But let's create the Battle Royale file here. I'm going to close everything else because we're only going to be working on this one for a little bit. Battle Royale, a linked list demo that simulates a list of players in a battle royale style game. We want the ability to build a list, print out all the players currently in the game, and knock out individual players. I'm going to say this as well. Later, we're going to add players in alphabetical order. Okay, made by me. My contact email. And what are we? We are in July 2020. Okay, so some of the things that I think I'm going to need for this, I'm going to include my standard input output.h, because I'm pretty sure this thing here saying print out all players is going to use the standard input output. The other thing that I know that I'm going to use, because I'm making a linked list, so I know that I'm going to do some memory allocation. So I will take my standard library. I'm not going to take command line arguments. I was thinking of throwing in some command line arguments just to demo it, but I don't think this example kind of needs them. So I'm going to have my int main void there. I might just put a return 0 in here. Not entirely necessary, the return 0. I often leave it out because I've done a lot of stuff where we never really used the return 0, and so it's not something that's always necessary. But anyway, okay, so I got my basics set up. Made sure I've got my main and my brackets there, so everything's going to compile at this point. Peter's asking, is create node predefined? No, it is not predefined. So if I want to use a function called create node, I'm going to have to build it myself. So we're going to build this whole thing from scratch. First thing that we are going to do is create a struct, which is going to be my linked list nodes. I might not even call this a node at the moment, because each one of these nodes represents a player in the game. So I'm going to call it struct player, and so that way when I'm working with these things, you know, I've named my variable in a way that's going to be easier for me to understand, because I know that these are the players in the game. So the struct player is going to have a pointer to another struct player. So remember, this is the variable type. Don't get confused with this star being attached to the word. This entire thing, these three parts here, is the variable type. So this means it's a pointer, and this is the type it's pointing at. It's pointing at a struct player, and a struct player is a variable type because we're declaring it as a variable type here. So this is a pointer to a struct player, and it's the next player. And then we are going to store a name, which is going to be an array of characters, and I'm going to set a fixed size for this. So if I want a fixed size for this, I'm going to have a constant for that. I guess we'll say max name length, just in case I'm going to have some other constants. So using something like max length is a little dangerous, because it's like, which max length is this? So max name length is going to make this super clear. We're going to make this quick. 100 characters should be enough. I doubt anyone in a game like that has a name that's longer than 100 characters. You'd have to be in the most convoluted clan ever to have like all these extra characters in it or something. Usually people's names are short single words, you know, 5 to 10 characters, but we're gonna have 100 just in case. So we're highly unlikely to cut off someone's name if we have 100 characters there. Then this will be our struct. So our struct is our variable type. We have made a new variable type called struct player, and anytime we declare a variable a struct player, we're going to have a pointer in it and a string in it. So struct player is our custom variable type that is going to be able to be used to store this information for us, this linked list node, which is going to represent a player. Next thing that we're going to do, remind myself with the slides, is we're going to make the function that creates the node. I'm actually going to do this simpler than it is here, because I'm not even going to be doing this safety checking that's here. Where are we? There. Okay. So I'm going to declare my function here. And so what I'm going to do is I'm going to say that this function called create node, oh no, not create node, create player, I need to think about what its inputs and outputs are. So player has this information in it. So what I'm going to say is, like, I want you to give me all of the information so that I can make this. So I'm going to say I need a player name. I'm going to call it player name here rather than the same thing as name, just so that we can differentiate, you know, better than player name. I'm going to call it input name here to say this is the one I've been given and this is the one inside the struct, so I don't get as confused. So this is the theory of naming variables, right? So you want a variable name that makes sense for what it's used for, but also something that distinguishes it against the other variables that are in the program. So it would be, if I was just saying what it was going to be used for, then name would make sense. But if I want to distinguish this against the name that's inside the struct, I can say this is the name that I just got given as the function input. So that's why I'm calling it input name. This is a little bit of a sort of background to why I renamed that just then. Then I'm going to need a next pointer, which is going to be a struct player pointer. So a pointer to a struct player, so a pointer to the variable player. And the name of that, I will use the same naming thing where I'll say input next. So when I set these things up inside this function, I'm going to know which ones were given to the function and which ones are part of the struct that I'm going to be creating inside the function. So my plan is I'm going to make one of these. I'm going to memory allocate it, which means the only way to keep track of it is to be keeping track of it via a pointer to a struct player. So I know that my output to this function, the thing that I'm going to give back when this function finishes, is a pointer to a struct player. So that is how we decide what the type of this function is. So this function is going to give me back a player pointer. It's going to take in a name and another player pointer. So this player pointer is what it should be pointing at as its next. The player pointer I return is going to be pointer to the node that I create. I don't want to leave this on its own because I want to keep this max name length, so I'm going to say the only input names I'm going to accept are going to have the correct length as well. Okay, so this is my function here. I've gone over my 80 character limit, so I might just do a really simple way like this, just for this function. Actually, if I want to be really correct about it, I could do it like this as well. Okay, so I'm going to copy this. I'm just putting white space there so that you can see it more easily. And then I'm going to say, all right, let's make this function. I'm going to comment here as well to say what this is. Creates a struct player variable in allocated memory. I think I'm trying to be technically correct in what I'm saying here. Returns, oh wait, uses the given input name and input next to populate the fields of the struct. Returns a pointer to the memory that was allocated. Okay, I'm being really specific with this. Right, I could just say returns a pointer to the variable that was created, but I want to make this really clear that I'm allocating memory for it, and then you get a pointer to that memory. So this is my way of saying you're not going to cause a memory leak here, because when I malloc something, you're going to get the pointer back. Okay, so I'm going to create a pointer to a player, and I don't really know anything about this player, so I'm going to call it P because it doesn't really have an identity at this point in time. So I've just created struct player pointer P, and so this is a memory address, and so if I want to get the memory to put into that address, I'm going to call malloc, which is going to allocate that memory. I want to know exactly how much memory I'm going to allocate, so I'm going to use size of, and the type of thing that I'm going to allocate memory for is a struct player, which is a variable. So struct player is a 2-word variable type because it's one of the custom ones that we made. So struct is the C keyword for human-made variable, in a sense. It's not the only one, but this is like, I made a variable called player. You know that this is something I made because I'm using this C keyword. So size of says, okay, I'm going to look at this, I'm going to figure out exactly how many bits in memory this thing is going to take up, and I'm going to allocate that many. It's going to allocate in bytes, actually. So this will give me a certain number of bytes of memory at a particular location. I'm storing the location here. So now I have done my memory allocation and I have a pointer to it. If this memory allocation doesn't work, there's a chance that it could fail. It's probably going to crash the whole program at that point. I do have some code here that checks for it, but I'm not going to bother putting that in because I have a feeling that this code would never run anyway. Where were we? There. Okay. So, assuming that I've allocated the memory, then I now have P. P is a pointer to a player that definitely exists now, but it doesn't have the correct input name or next pointer that it was supposed to have been given. So I want to make its name my input name, and I'm going to try something like this, but then I'm going to look at this and go, wait up. That's not going to happen because I can't take an array and just dump it into something. So I'm going to need to either, with a numerical array, I'd have to loop through and copy the numbers in. With a string array, at least I have some helper functions that are going to do that. So I'm going to grab the library that has those helper functions, string.h. So you can see, like, I'm building up what we're doing here. We're now using 3 C libraries for our program. So there's lots of stuff that we're doing that we've just sort of learnt in bits and pieces as we're going along. So I know that I want to copy this name here into this string. So I'm going to use string copy. String copy copies the destination is the first variable and the source is the second variable. If I was definitely unsure of that, I can always look it up. Destination is the first string. So you can see here they're using a character pointer as a string. So the character pointer being a string is very similar to saying that an array is a memory address, and so you can use a pointer and a memory address, which is the array, as equivalent of each other. Okay, so I know the destination is the first thing in there, so I know that the name field inside the struct P, so P is a pointer to one of these, which has a next field inside it. So if I did, if I want to get to the field inside and I have a pointer, I use the arrow. So P arrow name says follow this pointer to that memory location, find the field inside called name, and that gives you access to it. And I'm going to copy over that piece of memory the input name that I was given here. So now I don't need this line. So this is me saying create it, populate the name with the name that I was given. Then I'm going to take the new player's next, which hasn't been set up yet, so that has no value in it, and I'm going to overwrite that with whatever the input next was that I was given. So input next is a pointer. I know that because it has been declared as one of the inputs as being a struct player pointer. So this is the type, and this is the variable name. Don't get this confused and think this is the type and this is the variable name. We know that we would never start a variable name with a star. That actually is like illegal C, it won't run at all. So we know that if this can't be part of the variable name, it must be part of the variable type. So the variable type is a struct player pointer, and its name is input next. Now we have populated the variables, the fields inside the struct, so we know the struct is complete and ready for use. If it's complete and ready for use, we can return the pointer to it, which is going to mean that this allocated piece of memory will not get lost because we're giving back the address of it as a struct player pointer, and we know that P is a struct player pointer because we declared it as a struct player pointer. So we're returning the correct thing from our function. So now what we have is the ability to create a player. I'm going to save this and compile. I'm just going to call it battle, just to make sure that my syntax is correct at this point. So we're probably going to get some syntax errors here. We didn't. That's a little scary, because that means that the errors are somewhere else, if there are any. Oh, then again, I haven't written that much code yet, so hopefully this is correct. So this is going to create a node. So what we then want to do is build up our linked list, and we're going to use the really simple linked list that we did before, where we have a player pointer called head, and that's going to be the start of our list. And what we're going to do is call create player, and we're going to say the first input was the name, and the second is next. Next is going to be null for the first player that's created because there isn't anything else to aim at. And let's just let's put chicken in as the first player. So first player is chicken, and then we're going to add another player to the list, and I'm going to do it in the same way that I was doing it before. So I'm going to call create player, and create player is going to make the second player. I'll be the second player. And then, in order to link these two together, I know that head is pointed at chicken's node. So I know if I point at head, then I'm going to be pointing at chicken's node, so chicken is my next now. And so once I have said my node is pointed at what the current head is, which is chicken, I need to then move the head pointer to me. So I'm now the head of the list. And we can keep doing this to add other players to the game. Who's in chat at the moment? Dean's in chat, so Dean's going to join the game. So now Dean's the first element of the list, I'm the second element, chicken's the third element, and we can just keep building the list like so. Yeah, Dean's going to be in the help session, so if things are confusing here, you can go talk to Dean. So I wonder, I've got like 1 minute left. I at least want to see if I can create the function to print out the players, because that's a pretty simple while loop that was in the slides as well. So let me create one more function here, which is going to be a void function because it doesn't need to any program output, but it is going to send some text to the terminal. This is going to take in a player pointer, and I'm going to say it's going to take in the list of players. So let's take this down here, and that's a function, and I'm going to say print out the names of all the players in player list. And so in order to do this, I'm going to start with a pointer. So what I might actually do this time is I'm going to take a copy of that pointer. Player pointer, I'm going to call it current, because it's the current player that I'm looking at. This is the thing I'm going to use to loop through the list, is equal to player list. So the interesting thing here is I'm taking a pointer to the whole lot, but it's actually going to be a pointer to the head. It's pointing to the first element of the list. And so I'm going to say current is the first element of the list, and then it's going to move through the list. So my while loop is going to stop when current is null. So I'm going to say if current isn't null, then we're going to loop. If current becomes null, we're going to stop looping. So if current is not equal to null, we'll stop looping. Then the way that we're going to iterate through the list is going to be current is equal to current next. So that's saying that the way we're going to move is we're going to move the pointer to the next node every time. And so in this, what we're going to do is we're going to just do a print f. Actually, let's do an f puts. Just using these because it's handy to know about them. So f puts is going to take in the name of the current player. So current is going to be aimed at a player, and I want to get their name, so I've got to go the arrow to look inside the current node for the player, and f puts is going to put this to the standard output. I think that this loop is all we're going to need here. I might actually also do a printf here so that I have a new line on the end of that. So each name is going to be one per line. I think that's all I need in that, because I'm going to loop through and I'm going to print them out. And then let me come up here and I will do print players, and I will give print players the head of the list. And so let's see if this works. Hopefully if this works, it will print out Dean, Mark, and Chicken. Let's compile this and then run it. Right, okay, so what we've got here is we've got the ability to create a single node, and because these single nodes allow us to put pointers into them, we can link them to each other, because the first one is the head, then the second one aims at the head and becomes the head, next one takes the place of the head. So each one that we add after Chicken takes the place of what was in the head before, and what was there previously gets moved one further down in the list. And then we can print them out. I'm going to wrap it up there because we've just gone past 6 p.m. But if you have any questions about this, and I'm sure some people have questions about this, you can stick around afterwards. We were going to look at fgets and fputs, I think. I think Roy was asking about that as well. But for the moment, we'll call the lecture there, and I'll go to break for a couple of minutes, and then we'll come back, we'll answer questions, we'll talk about this if anyone wants to stick around. Okay, see you in a sec. Alright, I'm back. Catherine saying, gotta go, but we'll watch the extras when I watch the lecture again and again. Yeah, this is the point, I know this is the point where people start re-watching the lectures because there's just so much to learn because we start to piece together a lot of things. So a couple of things people were talking about there. Somebody said, where was it? Someone said something about freeing those memory allocations, and you were definitely right. I haven't cleaned up this properly. So if I wasn't rushing to try to get this finished so that I could show you a bit of the use of linked lists code, I would usually have created something that would clean up all of the memory of these before I started doing stuff like printing it out. So I would say, okay, I've got a whole list of nodes, and I need to go through them, and I need to free them all. Having said that, that's actually a non-trivial piece of code. So that's definitely going to happen next lecture. I'm going to explain how to do it, and then we'll do it. So I won't bother about freeing it right now. Okay, Terry was wondering about... Oh, okay. It's because this is not a struct. So notice there's no curly brackets. This is a function. I mean, maybe it would be... I know that it goes over the 80 character limit, but maybe it's more readable if I just leave it like it is. Or I could do some other dodgy stuff to shorten this. So I'm gonna let's try this. Okay, I'm gonna do a global replace of max name length and just call it max name. There you go. Now I've dodgily shortened my my function declaration there by shortening one of the names. I don't always suggest that you do this, but seeing as my active code review that I'm getting from you is that this is a little bit not so readable because everyone's used to the function declaration and the first line of the function being only on one line. When I split it, it made it look like I made two structs, whereas this is a function. The way that I can also do this is I go structs functions like so. And so that makes it a little bit more clearer that, I mean, there's only one struct. But there's multiple functions. So we can do this, where it becomes a little bit clearer if someone's reading this going, okay, this is where this stuff is, and then the main appears here. And I think I confused both Terry and Jed in that, because Jed's saying, what's the difference of the first and second struct? And it's like, the second one wasn't a struct. The output of the function is a struct player pointer. Yeah, so that's good. Getting your feedback there shows me that I have written something that was a little bit hard to read, and it's caused confusion, so hopefully this helps a bit there. Shayak's asking, are linked lists usually built last to first? No, they're not usually built like this. This is the only way I can build a linked list by only using the create player function. So if I want to do this with the minimum number of functions, then I would create it like this. When this example gets to the other end, when we're doing insertion in alphabetical order, then we'll see that we're not going to build it from end to end. We're just going to insert things, and we're going to use a function that's going to find the right place and insert things in between each other. But again, just the idea of inserting elements in between each other is super complex as well, so I want to talk about how to do that before we do that. Because you think about it, I said, okay, you can squeeze things in between each other, and then you've got to move all the pointers around so that they link up again. We're going to talk about that in detail when we do it. So for the moment, I'm saying, if we only have a create player function, how would we join a list together? Well, the only thing that we can change is the next pointer of the one that we're creating as we create it. So that's why it always goes on the front, because then we can get it to attach to the head and get the head to move to it. UG, it thinks that Chicken is definitely going to win with what looks like a Super Soaker there. Oh, Jed was the one who was saying, Malik, do we need to free it? And yes, that was correct, we did. UG is saying, what does line 54 do? Ah, line 54 moves the pointer. So, when we're looping through this list, let's go back to here. So, I have this list here that starts as head and could move through these numbers. So I'm just going to make this new pointer here, which I'll use green. So, the first thing I'm going to get when I'm looping through a list is, this is my current pointer. So current is a copy of the head, and we can see that here because this gets given the player list, and the first time it gets called, it gets given head. So we're going to give a situation where the pointer that it gets at the beginning is the first element of the list, which is the head of the list here. So this is the current pointer. So the current pointer here is pointed at the first element of the list, the head, and then let's step through the while loop. So current is not equal to null. Yes, it passes that, so it gets into here, and then it does fputs. Fputs is going to say, I'm going to take this string, current name, and write it to stand it out. In this example, that writes Dean there. Let me just, oh, I can't shrink from that side. Move this a bit so we're looking at that as well. So it prints Dean, and then a new line, so that means the cursor, if we could see the cursor, would come down here. And then current equals current next. Right. Let's see what current equals current next is. This is current. Current is, actually I'm gonna write it on this side. So this is current. So this is the actual variable, and it's going to store a value. And for the moment, that value is represented by this arrow that aims here. I'm going to get rid of this one because I don't want two of them. So now if I say current is equal to current next, so this is current, this is current next. So if I say current next with the arrow, what I'm going to get is I'm going to follow this to this node. This node has a next that points to this node here. So if I'm saying set current to current next, this is current next. It's like this arrow here, which is aiming at this, which means what I'm going to do is I'm going to use this value here, and I'm going to set this value to current, which means I'm going to replace whatever memory address was in here with the memory address of this node, because this one had a pointer to this node. So this is going to disappear. And it has now been replaced with this. So current equals current next moves the location that the current is pointing at from this one to whichever node was its next. And the next time it happens, this arrow is going to move to here. The next time it happens, this arrow is going to move to there, which is not really a location, but it's going to point at null. And then when it points at null, current will be equal to null. It will fail this, and it will pop out of the while loop. So hopefully that's a bit of clarity on what current equals current next does. So you've got to think about this happening in order, where the first thing it does is it reads what is the next pointer in the node it's currently looking at, and then it says, okay, I'm going to change my current thing that I'm aiming at to be this. So it's no longer going to be aimed at the node that we were looking at when we were getting all this stuff out. It's now going to be aimed at whatever this node said was the next one in the line. Pooja is asking, is next a variable name? Kind of. Next is a field inside the struct. So we would consider when we create a struct, so this is the declaration of the variable type. Then when we make one here, we memory allocate for a struct, and then we have a pointer to it. that's the variable there. And then we consider the name to be a field of the struct variable. So it's just a slightly different, but I mean the field can be treated just like a variable. So when I say take the pointer to the variable, go inside the struct, grab the name will be a string because it's declared as a string here of size 100. I can then use it anywhere I would normally use a string. So you could nearly think of it as a variable. You think of it as a variable that's part of a struct. But it's kind of not a variable in that it doesn't have its own name. The unique name is in the struct itself that's been created. So for this one, the unique name is P, which is the pointer that points at it. I mean, technically when you think about it, when you memory allocate, you never name this variable. You only name the pointer that aims at that variable. And then once I return this pointer P, it turns into something else. Because it becomes, like the first time it becomes head. And then the next time it has no name at all. It's just the next of, like, chicken's node never has a name. It's going to be the next of my node. And that's the only way we'll refer to it from then on. So I hope that helps. That next is kind of a variable. You can think of it like a variable. You can use it like a variable. But you can only access it by saying, I have to use the pointer to the nodes, which is the P is the pointer to the node as it was being created. Current is a pointer that moves through the nodes, so at some point it's going to point at a node, and then you can get the name out of it. So we call them fields because all of the nodes, all of the players, will have a name field. And each of their name fields will be a separate piece of memory where they can store information, so very much like variables, but they don't get their own name. You know, so we won't have like the name like I don't know, X or the name I for, you know how we had int I for our looping variable and stuff like that. We won't have that. We'll only have it is the name that's inside something else. Alex is saying, what does the arrow thing mean? Like current equals current arrow next. Okay, so the arrow says the thing that's on the left of the arrow is a pointer. The arrow won't work unless the thing on the left of the arrow is a pointer. So if this is a pointer, what the arrow does, let's say, so current arrow, the arrow says follow current to a memory location. So this is the memory location. And so I say, if I say current data, so if I want to say, hang on, current data, because this was the data was the integer inside. What that would do is it would say, okay, follow the current pointer to the memory location. Look inside this memory location for a field called data. In this case, the field called data has a 2 in it. So current data is 2. So what the arrow does is it says, this pointer is giving me a memory location, but the person doesn't, or the program at this point, doesn't just want to read what's in the memory location. It wants to read a specific field inside the memory location. So if it wants to read a specific field inside the memory location, it says use the arrow to get to that memory location and then pick out a certain part of it. So we're going to ignore this part of it and we're going to read this part of it. So we're going to pick out a certain bit of that memory. So the pointer takes us to the entire struct, but using the arrow says I'm going to go inside the struct and look at one particular part of it. So hopefully that helps, Alex. Liang is asking if this code will be uploaded. Yes, I will upload this code. Oh, another thing, talking about uploading stuff, I'm a bit behind on uploading things. Lecture 9 got corrupted, and I've been trying to fix it, and if I can't fix it, what I will upload... I mean, this one kind of doesn't mean anything to you because everyone who's here on YouTube at the moment seeing this is able to see YouTube. But anyone who's not seeing stuff on YouTube and is looking for stuff on Echo 360, if I can't get lecture 9 fixed, which is looking likely at the moment, it's like really weird because I can view it on YouTube, but I've downloaded it in several different ways and it's always broken. I will upload last terms, which is the same content, but a different video. So hopefully that's enough that people will still be able to see it. Liang's laughing that I'm still 81 characters. Is it where? I have one line that's going over there, don't I? Yeah. Oh well. I'm going to accept that, because that's only just over, and it's still reasonably readable. Yeah, and I think I confused people by splitting the lines, so maybe it was better to keep that. I think sometimes when you do it, instead of just doing the 4 there, sometimes it's good to spit it all the way out to here, so that people see that that is there. But it's always, there's never any kind of really solid rules for how to split lines, because it's like, how do you think the humans reading this are going to react? And then you got to split lines in a particular way. Yeah. So anyway, I will have videos uploaded, because I don't think I've uploaded to Echo 360 any of the week 6 bonus stuff either. So I need to upload that stuff, and I will upload this code as well onto the web CMS. So it looks like we're done with questions now. If you want to go over this in great detail, and I'm sure there's plenty of people who do, the help session is available now. I think the help session is going to be not super busy at the moment because our assignment's already finished. So if you wanted to really have a good look and spend like, another 15-20 minutes with Dean talking about this in person, asking specific questions, you can totally do that. That'll work. And for anyone who's interested in just like a little bit of like a social thing, as I said before, Dan Mansfield and myself are doing a stream tomorrow after dinner, so that should be a bit of fun. So I'm just gonna say goodbye. Chicken's gonna say goodbye. She's not gonna say goodbye. Oh wait, maybe a little. She's like totally comfy because she's got a lap now, so she's nice and warm. So I will see some of you tomorrow night. Obviously it's not course content, we're just going to be talking about things, so come along only if you want to. But I'll see some of you tomorrow night, and everyone else I will see next Tuesday when we continue this example, because obviously we're not finished with this example. There's plenty more we're going to do with this. I'm going to talk about things like inserting and removing from lists and things like that. We'll probably look at cleaning our memory properly as well, because this is just a memory leak at the moment. Yeah, and so we will add to this as we go along. All right, see you all soon.